Okay, hello everyone. My name is Ilya Eremin and I'm going to present you a talk on the novel features of superconducting magnetic structures with magnetic skyrmions. My name is Ilya Eremin and I'm going to present you a result of the collaboration together with Anatoly Volkov and Sami here from the Ruhr-University Bochum. And the results which are published are summarized in this free publication, plus we have also some recent results which are still in the process of writing. Okay, so when we are talking about heterostructures involving magnetic skyrmions and superconductors, you may naively say that it's an interesting from a point of view of a superconductor, but actually it is not true, because what is known that once we have a heterostructures involving inhomogeneous magnetic texture of various kinds, we know that the superconducting Cooper pairs, even if they are in the spin singlet state inside the S-wave superconductor, they are transforming into the long-range triplet component inside the ferromagnet, and this long-range triplet component can penetrate over the long distances, which basically also means that the spin transport inside the magnet will be changed in a significant way by the presence of the dissipation and less spin transport. Therefore, this kind of heterostructures are interesting, especially with magnetic skyrmions, not only from the context of superconducting community, but also for the community working in the field of spin transport. Now, another interesting discussion that has been very active over the last years is that skyrmions can also be a potential host for realizing Majorana fermions by the virtue of the presence of the both exchange field and the encoded spin-orbit coupling from the skyrmions. If it is transferred into the spin triplet component inside the superconductor, then one can show that the superconductivity in this case becomes topological, which will host then Majorana fermions, one in the center and one on the exterior of your skyrmions. So it's an interesting avenue. There is, however, a problem in this aspect, is that all the calculation has shown so far that you need a higher winding numbers. Yet there is another interesting aspect, apart from this dissipation and spin transport, and also as a host for the Majorana fermions, is that in a superconductor as well as in a chiral magnet, you have also two different types of topological defects. In a superconductor, we know that once we apply an external magnetic field or by the exchange field of the ferromagnet, we can create vortices, superpositive vortices, while in a chiral magnet, we have a below coordinate skyrmions, which are topological defects with a different winding numbers. Now, it's also interesting that vortex core in topological superconductor can also bound Majoranas, but the problem is that there is a problem to control those individual vortices. So the idea is that you can now try to connect skyrmions and the vortices and to make this as a platform for realizing composite topological defects, which also might be interesting from, for example, from the context of creating Majoranas, or by generally by looking into the spin transport by manipulating vortices. Now, an important part here is that, of course, one of the potential problems in this business is that the coupling between a ferromagnet and a superconductor needs to be relatively weak, because otherwise ferromagnet will simply destroy the superconductivity by the strong exchange field. Therefore, in contrast to the previous consideration, what we first did is we looked on the coupling only by means of the straight fields, in contrast to the previous consideration by Halsetal, where they consider proximity effect. We first look what happens if you put basically an insulator in between, and such that you avoid the direct proximity effect, but instead you have an interaction via the straight fields. Okay, so this is a heterostructure that we studied theoretically. You have a superconductor, which if you apply an external field, you can have vortices, and you have a chiral magnet. And also we know that due to a variety of the systems that you can have, you also have a range of fields where you can have skyrmions around the same values of the field, that you can also have vortices in a superconductor. Okay, So now we don't have any proximity, and we only assume that the means of coupling is electromagnetic coupling. So basically what is relevant here is that you have a vortex field which comes out of the vortex, and the magnetic stray field which is generated by the skyrmions. Okay, so in order to get information about the vortex field, what you just need to do, you need to solve simply the London equation. In the thin films, when the penetration length, London penetration depth is much longer than the thickness of the superconductor, you don't have simple abricosal vortices, you have so-called pearl vortices, and its characteristic length is determined by the lambda L squared divided by the superconducting coherence, and then you have a pearl length, and typically it can extend up to 1 micromillimeter in thin film superconductors. So at the same, and the also important part is that for the pure vortices there is a long range vortex field. Okay, so this you can do, and now assume that you have an information about the vortex fields. And so the next step what we did is that once you have this vortex profile, it basically introduces Zeeman coupling to the profile of the skyrmion and the chiral magnet, which you can basically put as a sort of a Zeeman coupling, which is couples to the skyrmion magnetization, and for the n you can take for either Bloch or near skyrmions and consider their coupling between them. Okay, so once you've done this, basically you can also see that the interaction energy is different for near or for Bloch skyrmions. But the first thing that you would like to know to study is that this energy is overall lower in the total energy of the system, and of course it depends on the polarity of the vortex. And indeed that for the particular polarity, for the negative polarity of the vortex, you see that for both, for the typical length of the vortex much larger than the skyrmion radius, or lambda much smaller than the skyrmion radius, you always see that the total energy of the system is lowered. So which basically tells you that whenever you have a skyrmion and whenever you have a vortex, they basically would like to attract each other and would like to stay in contact with each other, and that provides an attractive interaction. Now, for anti-vortices for different polarity, you will have a repulsive interaction. Now, okay, so once you have shown that there is and this we have shown in 2019, once you show that there is attractive skyrmion vortex interaction, it actually turns out that it can also be a nice platform for Majoranas, and in this case you can actually use a winding number which is more realistic, where winding number of n equal to 1 for the skyrmions. And of course, another possibility is that having such a combined topological defect helps to manipulate Majorana for braiding. And another interesting investigation that has been done also last year is that in principle, of course, you have a once you apply an external electric field, try to manipulate your skyrmion vortices, there is basically a competition between the Lorentz force, which is acting on the vortices, and the skyrmion Hall effect. And so it means that by having this composite topological defect, you can essentially compensate the skyrmion Hall effect, which is also another interesting platform for changing the properties of these defects. Okay, so now I mentioned to you that we have shown that creation of vortices lowers the total energy of the system. But of course, you need to understand that there is a total magnetic flux, and you have an imbalance of the magnetic flux compared to the flux carried by the skyrmions. So, which basically means that, of course, you will never have a creation if you have a ferromagnetic connection to the superconductor. You will not have just creation of simple vortices. You will have pairs of pair vortices, anti-pair vortices, in order to compensate the total flux. And you can compute the system by basically populating your thin film with skyrmion and the vortices and computing the total energy of the system and trying to find the most convenient configuration. And what we have found is that in this case, what you will get is kind of triangular lattice for the skyrmions, which is shown here by yellow, and which is hosting one or several skyrmion or vortices of one polarity, and the vortices of the other polarity will be sitting outside of this skyrmion. So this would be the most energetically favorable situation. Okay, so such that we also have a total flux equal to 0. Now, the other interesting thing is that you can further analyze in this case and shows that actually, in contrast to including a vortex-vortex interaction and looking at the total energy, it actually turns out that although originally for a single vortex and the skyrmions, both were energetically favorable, so that the total energy was in both cases seemingly minimized. However, if you diagonalize the entire system, it actually turns out that the only energetically favorable situation occurs when the size of the vortex is much smaller than the skyrmions, which basically means that actually such a coupling of the skyrmion and the vortices occurs only if the length of the vortex is smaller than much smaller than the length of the skyrmion. So it's only for large skyrmionic objects, but not for small skyrmions. Now, since we have made this prediction in 2019, there has been a realization this year by the group of Christos Panagopoulos, and he's giving a talk on this conference about this. So, which is exactly following the recipe that we have proposed, that you can take a current magnet and a superconductor, and there is a great level of scientific achievement that Christos and his collaborators made, where they have indeed obtained the necessary condition that various values of the skyrmions and the typical lengths of the per vortices is much smaller, in order to realize that you basically can have the situation, and they successfully confirmed that there is an attractive interaction between the skyrmion and the vortex. Once you understand this, it basically means, so what else can you do with such an object? And now I haven't mentioned much, but most importantly, the main interaction that has been playing a role until now is stray field of the vortex. We have made the inclusion of the stray field of the skyrmion, but it hasn't been playing an important role in total stabilization of the energy. But there are certain situations where the stray field of the skyrmions will be critically important for the superconductor. Okay, so for this we suggested to look into the specific situation where you have a ferromagnet, which was chiral skyrmions, and you have a two superconductor above and below. And we again solve the problem, but now what is important, we said that superconductor is basically far away from being in type 2. So you have a type 1 superconductor, and so there are no vortices, but essentially your skyrmion produces stray fields, and the stray fields generate Meissner currents in the superconductor, and basically there is a reduction of TC. And you would like to understand what will be the effect of the skyrmion on this superconductor. So what we found out is that the first important thing is that there will be a critical difference between the Bloch and near skyrmions. So while in case of the Bloch skyrmions, the stray fields appear to be symmetric for the upper and below superconductor, if you do the calculation, you actually see that for the near skyrmion, the stray field, or basically the currents, this Meissner currents, appear to be asymmetric, which will result in a different suppression of the superconducting transition temperature in the upper and below superconductor, which will be one effect that one could be able to see. And that would be another indication that you are dealing, for example, with near type of the skyrmions. And another interesting effect, of course, now in the context of now for how does presence of let's say this skyrmionic texture, how does it affect the spin transport? And here, of course, it's important that you have an inverse proximity effect. Namely, if you have a skyrmion, so now, okay, so now we have introduced proximity. So now our superconductor and the ferromagnet are not interacting any longer by the virtue of the stray fields. They really, there is a direct proximity between them. And what is known is that once you have propagation of Cooper pairs from a superconductor to a ferromagnet, we know that in the ferromagnet they build up a triplet pairs, and what is important, they will be essentially, there will be Cooper pairs which form at the boundary. And so what is then happening is that there will be an image of the ferromagnetic ordering, so the magnetization will build up at the surface of a superconductor, which will be opposite to the magnetization which is present in a ferromagnet, which actually means that any magnetic texture induces magnetization in the superconductor, which means that once you have a skyrmion here on the right-hand side, you will have superconducting skyrmion, so you will have a magnetization, so that built in superconductors, but will be a Cooper pair magnetization, which will be built in the middle. And what is interesting is that what we proposed is that you can use this effect to look into the Josephson current. And again, in the heterostructure, which involves superconductor ferromagnet superconducting, you can look at the Josephson current, which can be used as a measure to measure the type of the magnetization in this ferromagnet, which will give you another source how to determine the magnetization structure in your magnet. So, for example, you can, in principle, determine what kind of magnetic texture, like this, for example, magnetic skyrmion or the main wall, what will be, in this case, appearing in a ferromagnet. And one of the direct way to look into this is basically to look into the Fraunhofer pattern in the magnetic field. So you can basically see a distinct pattern for magnetic skyrmions, which should be visible in this case. Okay, so this is the end of my short presentation. So our main result is that we have shown that in the absence of the proximity effect, skyrmion vortices in heterostructures will interact attractively, depending on the polarity of the vortex and the skyrmions, which means that even in the absence of the proximity, there will be an emergence of topological hybrid structure. And this topological hybrid structure is interesting from many perspectives, and one of them is basically as a host, potential host for the Majorana skyrmions. There is another interesting effect, namely, which is much less explored, namely that the presence of the skyrmions and the penetration of long-range spin triplet component into the ferromagnet will basically change drastically the spin transport inside the magnet, and that will be another interesting property that one has to look farther in the future. What we have shown also is that the stray fields and the Meissner current induced in a superconductor will be asymmetric for the near type of skyrmions, which means that there will be a different temperature above and below skyrmion. And at this point, I would like to stop and thank you very much for your attention.